Okay, so we're going in to the next chapter, which is chapter 9, designing the database. A lot of this is going to look a little bit familiar to you from the 350 class, from the analysis portion, because I focused less on the class stuff and more on the entity relationship stuff. With that said, we're going into more detail. This isn't just a rehash of what we did during 350. We're going to be talking about things like normalization. We're going to be talking about things like data types in more detail, but you'll certainly see the continuation from 350 where we talked about databases and thinking about how you might store the data. Now for the deliverable, when we get to the milestone portion of this, we actually are going to be doing something beyond the transition from the so-called logical ERD, which is what you did in 350, and the physical ERD, which is probably the main deliverable here. I believe that will take most groups about 10 minutes. Unless there were major structural changes needed, then it might take you more time. But it's certainly not a massive change. So there will be something in addition to that, which will be the script. I do want to see the script for the creation of the database, and I'll be talking about that. I'm not sure if you have ever done anything like that before, so that will be an additional lecture that we'll have. Normally we do lecture, case, milestones, kind of been our pattern so far this semester. So this will be a little bit different, where I'll do lecture, milestone, lecture, case, mini lecture, milestone, if that makes sense. So a little mix, because I don't know what you guys have done in SQL before in creation of SQL scripts, and I have to make the assumption that there's at least one of you in here that the answer to that is nothing. And assuming that's the case, that's what I have to go on, because there is no prerequisite, database prerequisite for this class, so I have to come in and just show you how to do it. Now, fortunately for you, this is a very small part of SQL that you'll be doing. There's a lot, and as a matter of fact, I'm not sure if you know what it stands for, but SQL stands for Structured Query Language. And a query is only one of the things that you can do in SQL. It's weird that they call the whole language, this query, when it's only one of the things you can do. There's many other things you can do, and the query is actually not one of the things that you will be doing for this. That's the hardest thing, by the way. There are almost infinite permutations of what a query can look like, and there are entire classes devoted to how to write effective queries, joining tables together, the Boolean logic that goes into it. It can be quite complex. What you'll be doing is the relatively simple SQL to just build a table. And the code for that, I'll just tell you right off the top, is create table. That's it. It's not that bad, but again, I have to assume that you've never done it before, so I'll show you how to do it and how to implement that and test it and all of that stuff. So that's how we're going to be doing this, just to take it a step beyond the 10 minutes that it'll take you to convert from a logical to a physical ERD. So let's jump into databases. A little deeper dive here than last time. So the overview of what this chapter is just kind of a view on what databases are, why we have them, the type of software that you need to run databases. These are DBMSs, or database management systems. These are software that run in conjunction with your system. The way it was done prior to the widespread use of DBMSs were what are called flat files. And flat files are simply just text files that you store the data in, that there's not a relationship necessarily between one given file and another given file where you might store data. Like you might have a file to store the orders that are put in for your company and another file that stores the customers. Any relationship between those two has to be hard-coded into your information system. And that can lead to a lot of problems. I know I've told the story before, but it's just so illustrative of this point, I have to share it again. And that's my first experience ever post-college as a developer. And my first experience ever post-college as a developer was with a company that used a language called COBOL, which used flat file systems. It didn't use a relational database. And here's the way they did it. Every time they would acquire a company, and they acquired many, many, many companies, thousands of companies, they would take the record, so record is just a line in a flat file of data. They would take the fields of the record and just tack it onto their master file. And so by the time I worked there, they had literally millions of fields per record, with 99.9% of them just being empty for any given line. That sounds pretty messy, because it is. It's extremely messy. And hundreds of millions of lines within this master file. So it was an interesting experience, to say the least. They gave this new guy, this 22-year-old guy that was just starting, the unenviable task of trying to figure out why random mailings were going out missing 1 or 2 digits from the zip code. In a 100 million line system with million field records, hundreds of millions long, can you just figure, and by the way, there was probably 5,000 people that worked there, and they just give this 22-year-old fresh out of college, to me, a fundamentally difficult thing, and it took me months to fix, but that's pretty old school. And what essentially all new companies do now, or not new companies, but new projects do now, is they use relational databases, because you don't run into those same types of problems, because it's built in a fundamentally and structurally different way. So a database, as it says here, is an integrated collection of stored data that is centrally managed and controlled. Integrated collection of stored data. So integrated, again, is alluding to those relationships between the different data sets. And the big point to this is that you dramatically reduce the amount of redundancy that data sets have. Centrally managed and controlled, that's not the way it always was. Again, in the previous semester, I talked about this concept of islands of information. And with islands of information, every subunit within an organization would have their own set of data. It was decentralized, which leads to essentially inevitable conflicts of data. You have errors all over the place. And there was this push to let's put it in one place, let's put it in one place. And we need to make it related to each other so we don't have redundancy. And then that's where this concept of relational databases came from. There is software, as I said, database management systems. And there's a lot of choices here. The 4 big ones are Oracle, SQL Server, DB2, and MySQL. And there's a lot of other ones, by the way. There's hundreds of DBMSs you can pick from. If you have a small, tiny little database that you're using for an app, you might use Firebase, for example, or SQLite is another one. But I'm talking about large organizations storing large amounts of data. There are scalability issues, and those 4 can handle pretty much any scale that you want to throw at it. The smaller ones I'm referencing, they couldn't. They would start to fall apart at a certain point. And then there's the cost question too. DB2, SQL Server, which is Microsoft, and Oracle charge large amounts of money for licensing. For a large system, you'd probably be looking at close to 7 figures in licensing, close to $1 million in licensing. MySQL is 0. It's free. It's open source. So what do you think is the fastest growing DBMS? MySQL, because of that reason. And there was a suspicion early on, so I'm going back probably late 90s, early 2000s. There was a suspicion early on that MySQL couldn't scale as well. It wouldn't be as robust as Oracle or SQL Server, and that has not proven to be the case at all. It has proven to be just as robust as the costly ones. A schema, this holds the metadata, and metadata is the data about the data. What does it mean when I say long interval? What exactly does that mean? Well, it means I'm using 4 bytes to store the data. Because there's going to be limits on everything, right? If I have 1 byte to store a number, what's the biggest number I can store? Anybody know the answer to that? I have 1 byte to store numerical data, that's not a floating, it's an integer, what is the largest number I can store? Well, one quick way to answer that would be to say, well, how many bits are there in a byte? Well, there's 8. 2 raised to that power gives you the maximum number that you can store, that -1. 2 raised to that power -1, so you have to start with 0. So 2 to the 8th minus 1 is 255. That's the maximum number I can store there. What if I have a word, a 2-byte word? What's the largest number I could store in a 2-byte word? Roughly 65,000 something. I don't remember the exact number. 65,536 maybe. It's somewhere around there. So you have to think about this. You know, when it comes to a schema, you have to think about what does it mean when we talk about discrete mathematics and limits on data, which essentially you have to have in computer systems. You know, how many bytes should I use for a name? Well, a byte in the ASCII encoding scheme, a byte stores a character, right? So in the schema, I'd have to say, you know, how many I'm going to use, or maybe I'll be fancy and I'll have a variable length, you know, a varchar, if you will, that doesn't take up, you know, useless space. So say I reserve 50 characters for a name, but I only use an average of, say, 15 or something. That would be a more efficient way to approach it. And then there's the last thing there, structured query language. I mentioned that, SQL. Some people call it SQL. I don't know why, but that rubs me the wrong way. I prefer SQL. This is the standard query language to access and update data in a relational database. So our core components, we have our schema data. Again, this is our metadata, our data about the data. The application domain data, this is the stuff that I'm actually storing. And over here we have the API SQL processor. Essentially, this where you have to have some type of language encapsulating the data. You very rarely directly access the data, you know, unless you're a DBA, a database administrator. If you are a user or even a systems type of administrator, you generally use the interface of the application to access that. Oracle really wanted to get in on that application game, and they actually, in their suite, they have an application development system that uses something called PLSQL, which allows logic, because there is no logic in SQL. There's only data descriptions. And then the queries, I guess there's sort of a logic with the queries, but you can't really do anything with it. It just kind of returns the data. You can't decide how to parse it or how to display it or anything. But so other than this Oracle API package, this is standalone code. You can have a direct SQL processor, as we'll see when we get to the PHP myadmin, that will allow you to go in and directly manipulate queries. Again, pretty rare to see that in an actual application. And then we have the administration interface. This is where a DBA would go in and maintain the database. So when it comes to, that's a lot of stuff there. I would say the most important thing for a system, you know, from a user's perspective or from a systems administrator's perspective, would be the box that says API SQL processor. That would probably be the most important box. They're all part of the system. They're all very important. But when it comes to systems use, that's what's going to be used. When it comes to systems development, you'll be using these two down here, the direct SQL processor and the administration interface when it comes to the development of that system. So you guys will be using that. But when you think of your typical user, so for you guys, you know, you have your committee project. Do you see a faculty member from art history going in and trying to create their own SQL query to have you know, the type of output they want? Absolutely not. They'll just say, hey, I want to see a report that does this. Can you guys do that for me? Which is normal. You know, that's what your typical user is going to ask. They're not going to go in and do it themselves. And then assuming there are still people working on it or maintaining the system that are willing to do enhancements, they would go and do the administrative stuff, those bottom two boxes, and then create the API for the person to have that report that they're asking for. So getting deeper into the database schema, again, this is the data about the data, and it describes how the data is stored. And in a database, the data is stored in a concept called tables. For your typical application developer, I always feel it's important to clarify what that word means, because to a typical application developer, tables mean something very specific. And what a table generally means to an application developer is that it's a temporal piece of data stored within the random access memory during the run of a program. So I might create a table that, say I'm reading in a file and I want to manipulate that file, so I'm going to read it in, put it into a table that I've created in my application code, which now I have much quicker access to than reading through the file. But if, say, the power is lost or something during the program run, that table disappears, right? It's not there anymore. It's in random access memory. They don't mean that when they say table here. They mean more of a logical view of a file. And physically, that's what it is. It's a file. It's an indexed file. So if I have my DBMS stores, say, 12 tables, and you do refer to them as tables, there are 12 actual files being stored and managed by that DBMS. Now, if you get to the deepest level administrator, so say a DBA, the DBMS, the software, handles all the work of those files through the schema. So I'm not worried about I/O, input output. I'm not worried about file reads. I'm not worried about any of that. I'm not worried about how exactly is the foreign key pointing to the exact memory location of a primary key in another file. That's not anything I'm concerned with, and that's actually the beauty of a DBMS, is that it takes all of that work out of the hands of the developer. Because when we used to have to do that with flat files, that was a big part of the workload. That was a lot to keep up with. And now DBMSs, they just do that. And you trust that they work, and they do work. So that's that second point there that I was talking about, the foreign key and the primary key. Those are the associations between the tables. And again, I use that term in a very careful way. I'm referring to it not as a programmer, but as a database developer. Details of the physical data storage, including types, lengths, locations. That's what I mentioned the first time the schema came up. This is the descriptions of the actual data types and what it means when I say, a long integer or a variable character. And the important part about this is that there is no de facto standard between different DBMSs. So if I create a database in Oracle, I can't take that code and just run it in MySQL or SQL Server. The schemas are unique and proprietary between different DBMS software. And that's pretty important, because when you make the call for what type of software you're going to use, remember when we did the architecture case and the milestone, and we're kind of looking strictly at hardware? Usually you look at all of the components, including software. We only had a day or two to work on it, so we couldn't do everything. But this is one of the calls you make, is what are we going to go with for the DBMS? What type of server do we need to run based on the number of typical users that we'd expect? What type of bandwidth do we need? So those, you go a little deeper than we did. I was kind of just exposing you guys to a small segment of the type of deliverable that you would have in the architecture portion. But honestly, you have to pick this, because this is going to inform moving forward how I build my scripts and all of these things for the SQL. Basic characteristics: simultaneous access by many users and many applications. Also, a beautiful part of the DBMS. So I talked about it, taking this file management hassle away from developers, which is awesome, and it really, really is awesome. This is another really cool thing: simultaneous access by many users and many applications. Have any of you ever written a multi-user system before? Okay, thank your lucky stars, because it is honestly pretty terrible to do in terms of you're trying to maximize how useful this thing is and also make it work right. And when you think about a multi-user system, just something simple like accessing data. If I'm customer service person X and I'm accessing a customer's record, and say they're updating their address, something simple. And at the same time, say this is John Smith, his wife, Jane Smith, also calls, and she wants to, say they have another house, a condo somewhere, and she wants to use that address. And they just say the husband and wife haven't talked to each other about what the address they're going to use is. And so they have these two conflicting things. They both call separately. Customer service representative X has gone in to make the change. From a technical perspective, what should customer service representative Y be able to do at this point? So X goes in at 12:01. Y tries to go in at 12:02. What should happen? Remember, they're both pinging the exact same record. What should happen? Yeah.
Why doesn't see X's change?
But X is in the middle of doing it, so they haven't submitted it yet. They have the file open and they're in the middle of typing in a new address as Y gets to it. So they don't see anything yet. All they see, if they could access it, all they would see is just the original information pop up on their screen, which is, from a systems perspective, probably not good, right? Because X hits submit while Y still has it open, and then Y starts to type in their change and click submit. How do you know what's going to happen? Yeah.
Should it say this is being what, John?
So what you're saying is a record lock.
Or just on the page say some other agent has this page open.
Correct. So that's a user interface description, but behind the scenes, what's going on is a record lock. And you're right. That's generally how it's handled. And setting that up in a custom-built multi-user system is very challenging. It's not easy to do, technically. And the DBMS does it for you. That's another beautiful part about the DBMS is it handles that multi-user access. A lot of you guys, you've been kind of spoiled. For example, you've worked in, say, Google Docs, and you're like, hey, my friend has it open and I have it open, or working on it at the same time. What are you even talking about? There's nothing that needs to be locked. The type of code that Google wrote to facilitate that is next level. It's beyond, we worked forever, not we, but the computer science community worked forever. We had this vision back in the 80s for, how can we do this? And it wasn't until 2010s that it became a reality, because it's not easy code to do. And it's essentially, it's a whole set of very detailed and precise record locking that they're doing, but it switches so quickly that it seems seamless to you. To you, you're looking at, oh, he's making a change, she's making a change. Oh, wow, look, cool. It works very, it's like we both have it open. You don't really, but it feels like you do. That's the perception, and that's why it's hard for you to understand, because it works so flawlessly for you, it's hard for you to understand why this is a problem. You're like, this shouldn't be a problem. It's a problem. And if you guys ever wrote code to support that, you'd see why it's such a hassle and why the DBMS doing it is great. You don't have to worry about it. It just handles it for you. All right. So what else does it have? Simultaneous access, direct access to data with a data interface. This is the kind of the DBA interface you guys will be using through MAMP. You'll be using the PHP MyAdmin, but if you're using Oracle, they have a command line interface that you'd use. It feels somewhat similar to a terminal that you would access, Linux or something. It feels, the Oracle one it's much more efficient, but probably less user-friendly. You tend to use scripts a lot more with that. But you guys are probably happy to be using a more graphical user interface that you'd see with PHP MyAdmin. But you need something, bottom line. The DBMS needs to give you some way to manage and administer the data. Uniform and consistent access, so it needs to be, the way that data is retrieved should be very consistent. Integration, distribution of data across multiple servers. So, database design and administration. really what a lot of this boils down to is that you must, absolutely must, design your database before you implement it. I'm teaching a 445 class that actually some of you in here are in my capstone class. And I will say the vast majority, if not just about all of the people in my development track, there's 2 tracks you can do. One is research, one is making something with code. And pretty much all of the people in my making something track are doing extreme programming or agile development, which is kind of code for, I just want to start working on it. I don't really want to waste a lot of time with all of the documentation that you do in a class like this, analysis and design. I just want to start building it. And I'd say that's a very common theme that you see among developers. To them, all this stuff, this design and analysis stuff is it's paper pushing, it's time wasting. They don't like doing it. And I get the feeling. I understand why you feel that way. And there are ways around it. Agile development and extreme programming are legitimate, real, and effective development methodologies. There's nothing inherently wrong with them, except when it comes to databases. You absolutely have to plan your database first. If you don't, it's just a mess all around, because you have to understand how the associations are built between the tables. You have to understand all of the tables that you might have. You have to understand the types of data you're storing, the attributes and fields within those tables, the types of data, and then you build a script around that plan. And when I give that little kind of mini short lecture on the implementation aspect of databases, I'm actually going to start with a mini design, because you have to. There's no way around it. And so even things like we have on this slide, it talks about, what is the overall architecture going to be? Is it just something that is one person's accessing and using, a desktop system? Is it a shared database? Is it, multiple servers? All of these come into effect when you start to consider how you're going to be designing your database. Thinking about who's involved. Is it going to be joint application development with the users and systems analysts and developers all working together? Managers, things like that. Who is the database administrator going to be? Database administrators are a very interesting breed, just because there's not many of them. And there's a desperate need in the United States for database administrators. And what happens with the laws of supply and demand when there's a shortage of supply and a high demand? Way up, way up. I worked with a hospital when I used to live in Fredericksburg, and it blew my mind. She told me, she being the CTO, Chief Technology Officer of the hospital, they couldn't find DBAs, they couldn't find database administrators. And so they were having to pay exorbitant amounts of money to consultants to come in. By exorbitant, I mean around $750 an hour for them to come in. And I said, well, what type of pay are you offering? Because I'm sure I could find some students that would love to do it. She said, well, we only can offer 120 starting. And I said, yeah, I don't think they would complain too much about that. So I'm still surprised that you're having a problem. And she said, well, the problem is, remember, Fredericksburg's about, depending on traffic, like 50 minutes to an hour south of the DC area, Northern Virginia. Said if they're willing to drive up there, they can earn 175. So to them, it's worth it to earn that extra money to make the commute up to Northern Virginia, and we literally can't find anyone, and there's not many to begin with. And I was just like, yeah, I see, it's still weird to me, because there's a quality of life question. And is anyone from Northern Virginia? You know what the traffic's like, right? And driving Fredericksburg to DC is like, I think it's the worst drive in the entire United States. I mean, I don't know if you can get, maybe LA and Atlanta, maybe they have some worse things. I lived there, I can tell you I avoided it at all costs. I hated making that drive. Because I say 50 minutes to an hour, let's be real here. 2 hours to 2.5 hours each way is probably more realistic. And to me, I'm like, 175,000, that would be wonderful. But I could probably make do on 120. I mean, to save the hours and hours of traffic. But she said, no, we put calls out for DBAs. We'll list it in like Indeed and all these various sites, and we'll get 3 or 4 applicants. 3 of them, they know what a database is, and that's it. They took like a class in community college for, database design or something. They never actually built any databases, but they kind of know what they are. So obviously they're out of the question. And then one person that's probably pretty skilled, and they come in hard on the negotiating and they say, no, I need 150 or I need 160 or something. And we're hard capped on the 120 because we're a nonprofit and that's just what we have. We have 120. And so then we don't hire them in that cycle. And then we have another year we have to wait to get through HR approvals again. So another year that we have to do these consultants where we end up paying the equivalent of like $400,000 a year in consultant fees. And it's just this, she seems so frustrated, and I'm like, I get it. And I started directing my students. There weren't many because I was in the business school, and technical skill level was on average quite a bit lower. But there were a handful here and there that I would direct there, and ultimately one of them did get hired. So I was like, okay, good. That worked out. But it was funny to see just that little microcosm, because I've read that there is a DBA shortage in security. Security analysts and DBAs are like 2 of the biggest shortage areas, particularly in Virginia. There's just a huge need for that around here. All right. Continuing with the DBA, they protect the database, manage multiple DBMS environments, maintain high performance levels. So they're looking to balance access, because if you don't, in normalization, this is where you're breaking it down to reduce the redundancy within the database. The more you normalize, the more processing cycles you have to join tables back together when you do queries. And so it's a balance of data and performance. Sometimes more data equals faster performance, but then you're using up disk space. So you have to kind of balance that and make a decision for what's the optimal area for normalization, and then you tweak as needed. That second point there, second subpoint where it says authentication, that one's interesting. That one's very interesting because, as I said, database management systems do not stand alone. They don't stand alone. DBMSs work within the context of a larger application. Therefore, the authentication is part of the code of that broader application, which is stored in plain text in the code. Now, if you're using a web-based interface like you guys are, you need a server-side script, and barely anybody uses CGI anymore. I don't know if you know what CGI is, but it stands for Common Gateway Interface, and a Common Gateway Interface allows you to write like .NET or Java or some more kind of typical language that you then compile. And compiled code, plain text doesn't matter anymore because it's compiled, it's an executable now. But interpreted code like ASP, Cold Fusion, PHP, which is what 99% of web-based apps are written in, or with those other, they don't use CGI anymore, they use these interpreted languages. You don't compile the code. The code is interpreted, which means the plain text for the authentication is just sitting there on the server. And we haven't really fixed that yet. So authentication, when it comes to the actual applied mechanism of how you access the database, to me, you guys are going to feel weird doing it when you write your first bit of code where you access a database. Have you guys ever gotten an email where they've sent you your password plain text? Like, I forgot my password, and I've gotten a couple of those. I'm always horrified, like seeing it, not in the hidden ... but actually seeing the word is just like, it's like if I saw a naked picture of myself just pop up on like Facebook, it would just be like stunning, like, oh my God, that's what it feels like seeing my password. And when you guys write your code and you write your password in plain text, it's going to feel weird. At least I hope. It should feel weird to you. That should not feel normal. But that's how you do it. You write it in plain text in the code. And interpreted languages, it can be interesting because it just stays there on the server in plain text. Relational databases. Another interesting thing here, pretty much any database class that you might take, they talk about all the different styles of databases. There's hierarchical databases, there's network databases, there's relational databases, and it always annoys me to no end because all the ones that are not relational databases are kind of more academic exercises. They are in no applied applications that I've ever seen. Past, say, 1978 or something. Earlier on, before relational databases became our de facto standard, yes, there were a few, but they don't really exist anymore. And I appreciate that this chapter doesn't dwell on these other styles of databases. They strictly go into the relational database because that's all that's used. So what is a relational database? Again, we have this logical view of a table, which is a two-dimensional data structure of columns and rows. A row says one horizontal data, okay. But what is a row really? Yeah, that's technically what it is. But if you wanted to describe it to a layperson, what would you say? What would you say the row part of the table is in a database? To an organization, to a manager in an organization. So a non-technical guy or girl, you're trying to explain to them what it is. Yeah.
Like a thing or an entry.
Entry, yeah, I like that. And generally, what are entries? Like, from an organizational perspective, what's an entry? Instantiation, yeah. A record, maybe. Yeah. So I think that's the word I like to use is record. Some people use tuple. I don't know. I've never quite gotten that one, but that's another word to use for a row. What about the columns? Interesting that the author doesn't define that. They define row, but they don't define column. They allude to it with that word there, attribute, because that's what a column is. A column is an attribute. And again, to a layperson, we would probably just say it's like a field. It's a part of the record that you're storing data. So if I had a table for employees, a row would be a single employee, and a column would be a unit of information about that employee. So if I had a row for me, there might be a column that says first name, and the data in that would be Michael. And that's that last point there, the attribute value, the value held in a single cell. This is something we did talk about last semester, the different types of keys. This is the thing that you use to identify a single tuple or row. Candidate key is a field that could be a key, but you don't necessarily say it's a key yet, but you say this could be a key. And the reason why it could be a key is for two reasons. Number one, any value in there is going to be unique. And number two, it must be filled in, so it can't be null. Those are the two things to make something a candidate key. Once you pick a candidate key, this is called the primary key. So this is the attribute or field that's used to uniquely identify a record in a table. The key chosen by the database designer to represent the relationship among rows in different tables. Foreign key. This is the field that I use to identify the relationship to another table. Every table has to have a primary key, at least one, sometimes more than one. Those are called composite keys. Not every table has to have a relationship, a foreign key. But if there is a relationship, one of the two has to have a foreign key. And so here we see all these terms I've been using. Obviously terms are easy test type things. Which of the following is the word for an instantiation of a table? Row. Things like that. So here we see a row, a tuple, or a record right over here, indicating an instantiation of that table. Up here at the top, we see the field or attribute names, and then a single attribute value down here. And generally, they're pretty straightforward, the primary keys. You see here, it usually say something like ID at the end, and you see all these unique values. And here is the logical representation of the association or relationship between classes or entities. So we have production item and inventory item with a one-to-many relationship between them. So this is something we did cover before. And then we see the illustration of that where we have product item ID in the top table for the primary key. And then in the inventory table below, we see the foreign key for product item ID that would link back to the product table at the top. One-to-many is the type of relationship that we're going for, and the way you assess that is when you're doing your design, you ask both directions. So you have this association of this relationship between your two entities, and say, for example, you had, the classic one is customer and order. Can a customer place more than one order? So that's going left to right, and you would say yes. Okay, well that side has a many. Can a single order be placed by more than one customer? Say no, a single order ties back to one customer. Okay, so that's the one side. Now one to many, that's what I want, that's great, I can move forward. Sometimes you get, when you ask this question, because you can't go in with the assumption that it's going to be many to many. It might be one to one, it might be one to many, it might be many to many. You don't know that. So if I'm asking that question, that both sides thing with the relationship, and my answer is, this is a many to many. And the other class example I gave there are students and classes. Can a student take more than one class? Yes. Can a class be taken by more than one student? Yes, that's many to many. This is not allowed. So if I have a many-to-many relationship that I've identified during analysis, when I get into design, I have to fix that. And the way I fix that is by creating, I call them linking tables. But it says here, create a new table and add the primary keys of the endpoint classes as foreign keys and as primary keys. I like this description by the author because it's a little more explicit than the way I did it. And I think that students like explicit directions. They don't want to have to kind of, I'll figure it out on your own, and then they get it wrong. They hate that. Whereas this is very clear. So what it's saying is students and classes, let's say that the primary ID or the primary key for the students is student ID, and the primary key for the classes is class ID. So what this is saying is I take student ID and I take class ID and I put them in this linking table that now joins the two and make them both primary and foreign keys. So it's a very explicit direction in how I fix the many-to-many problem. Then we have the last one, one-to-one. Unlike many-to-many, these are not wrong, but it's pretty uncommon that you would ever have a one-to-one. Now, if you recall, I said that when you split tables, it takes a processing cycle to bring them back together. So the server, when you do a select and I'm saying, okay, I'm going to bring these two tables together, it's work for the server to do that. And if I have millions of users accessing that server at the same time, that work adds up and you end up with a slowdown. And not only that, but it costs money for the company because now they may have to have additional servers. They have to spend money. Literally, it costs money in electricity. You might be like, whoa, are we talking like a penny here? Maybe, but a penny times a million starts to add up every single day. So you better have a really good reason why you want to have this relationship. Because again, one-to-one means for every one of these, there's one of these. Shouldn't they just be one record? The one time, there is one time, you might be asking yourself, well, why do you even have as an option then if he's so critical of it? The one time that you might want a one-to-one relationship is if you have an optional relationship on the other side. So say, for example, I had a hospital with doctors had the option to have a specialty. Not all of them had it. As a matter of fact, relatively few doctors have a specialty. But it's going to be specialized specifically to them. So no one else can have that specialty. And only, say, 5% of the doctors have that specialty. So, and say there's 1 million doctors. I know this is a crazy situation, but I'm giving you the example I can think of. So if only 5% of them have it, this is, 5,000 pieces of data. And so what's going to end up happening is if I make that a field in a single table, I'm going to have 995,000, if my math is right. Maybe I didn't do the math right. Maybe I guess it'd be 50,000. So 950,000 blank fields and only 50,000 fields with values in them. So do I want all of those blank fields? If the answer is no, that's a waste of space. It just isn't a good way to do it. I might have a one-to-one relationship table off to the side where I only put a value in there when needed. See how I'm saying it's rare? It's this really convoluted description that I've had to say a justification for when I would want a one-to-one relationship. 9 times out of 10, if you identify a one-to-one relationship in your design, you say, okay, I'm going to make those one table. 9 times out of 10, maybe 99 times out of 100. That's what you would say if you saw that. But they're not wrong. They just don't make any sense. Key term here, guaranteed to be on the test. Referential integrity. That is something, I think I've even seen that on Jeopardy, which really blew my mind. I was like, I know that one! Referential integrity, yes, got it. And then they move on to like Russian ballet, and I'm like, oh man, I won't know any of these. Referential integrity means that for every foreign key value, there better be a corresponding primary key value for it. If not, I violated referential integrity. Real DBMSs do this for you. They will not let you enter data that violates referential integrity. Access, Microsoft Access, is not a real DBMS. And you talk to anyone that works with Access in the workplace, they will get very salty with you if you say that. Take it personally if you say that. They'll say, I work with a real DBMS, I work with Access. Access allows you to violate referential integrity, so no, you really don't. And my buddy that I used to work with, he did that for 10 years before he became a professor, and he got so mad at me because I would tell all of my students all the time that, and then they come into his class where he used a lot of Access, and it was interesting. So I guess, be cautious with your wording, but bottom line is it's not. Oracle, SQL Server, MySQL, DB2, they all maintain referential integrity. And if you try to enter in, say for example, you're trying to enter in a sale for a customer and you put the wrong customer number in, a DBMS will just tell you, nope, no customer like that exists. I actually just worked with a system just yesterday that I couldn't believe. It's 2021. How is this possible that such a terrible system exists? So I'm going skiing in a couple of weeks, and I'm going to this place called Bryce, and they have their own system to buy like lift tickets and stuff on their website. And I went in yesterday to put all the stuff in, and it was just errors left and right. It was like, I could tell that they were allowing violations of referential integrity. They must have an Access backend on this. I couldn't believe some of the things. I actually had to call, which is like so 1987. I was like, yeah, this is weird, but I guess I have to order this on the phone. She said, no, just keep trying. I'm like, no. I've already dropped like $400 on the hotel. I'm not going to just wing it and go up there and hope I can get lift tickets. Can you do this on the phone? Fine. And she was so mad the whole time we had to do it. It ended up working. But I just yesterday experienced this not working right, and it really blew my mind. I felt like I would tell you a story circa 1990 or something, but no. This is February 22nd, 2021 that I experienced that. All right, normalization. So what is the point of normalization? The point of normalization, well, with the exception of first normal form, generally the point is to reduce redundancy as much as humanly possible. That's why you go through the process of normalization. I did say with the exception of first normal form, and the reason why I'm saying that is generally to go from 0 NF, so 0 normal form, to first normal form simply means I'm giving this data structure. That's the big first step you make, is to give it basic structure. And the vast majority of database designs that students submit are in first normal form, just by default. As you go deeper down, this is when you start running into the problems of what costs more, processing or data? Because that's the trade-off you're making. The more normalized you get, the more you end up costing the organization processing. And it's a real question. What does cost more? What do you think costs more? Does it cost more for a company to have to pay for more processing or pay for more data storage? What do you think? I'm not expecting you to necessarily know it, just if you have like, I guess. And it changes too, by the way. It's not a consistent thing. If I asked you this question in, say, 1990, your answer would have definitely been the data. Yeah?
Processing right now.
Yes. Now it's processing, which means there's this economic pressure to not normalize. You definitely need first normal form, for sure. But to go into Boyce Codd normal form or fourth normal form or way deep into it, you're going to be costing the organization processing resources, which is generally the less desired of the two. You have to pay for one of them. Memory is insanely cheap now. It's almost to the point, in math, as you approach 0, you just eventually just say, well, it's 0. When you get to calculus and these types of things. That's almost what memory is in terms of cost. Cost per byte. Cost per byte is like 0.00000000001 cent per byte. It's very cheap. And now we have lying Intel telling us we're going to have 7 nanometer CPUs by 2015. That didn't happen. We're still at 14 nanometer. And what they're doing is they're changing their production lines to make this old tech, which is probably over a decade old by now, appear to be faster. I predict that Intel will be not gone, but a major second or third player by 2025. Within 4 years, Intel used to be the processor that you would pick. Like, you wanted quality, you pay a little bit more and get Intel. Maybe, if you're trying to cheap out, you go AMD or something. Not anymore. Intel is going to, again, not out of business, but way behind the ARM processors and AMD by 2025 for sure. So, which isn't good. I think more competition is better, because this question of cost for processing is going to continue to be an issue for organizations. All right, so let's look at each of the main 3. There are normal forms beyond this, but let's look at the main 3, which is first normal form, second normal form, and third normal form. Those are the main 3. So a table is in first normal form if every field contains only one value. So let's look at the first example here. We have Social Security number, name, department, salary, and dependents. The problematic field here are dependents, because you have an unknown number of discrete attribute values that are kind of in a single field, but not really in a single field. John, Alice, and Dave are 3 separate values, but we have them stuck into the single field, so this is not in first normal form. Generally, this is actually a pretty nice and clean example. Generally, when you're in 0 normal form, all of the data for the organization is just crammed into the single record. Kind of like my experience with my first programming job, like that. That was definitely 0 normal form. This is a pretty clean example. It's correct. It's not in first normal form. And I think it's good for students to see a nice, clear example of not being in first normal form. But generally, they're much messier than this. There's all sorts of collections of data all over the place that violate this concept of every field contains only one value. And you also do not want to vary the number of columns. Let's say Mary has a fourth child. How would the second table handle that? Could it handle that? There's only 3. So this is problematic. So the solution here, you don't want a varying number of attribute fields, and you don't want multiple values in a single attribute. Those make it not first normal form. So the solution to that is to put it in a separate table. And what we have here is we have a primary key, just record ID. This is pretty generic. I don't love that, but it's not incorrect. We have a foreign key here, so this is the value that points back to which, I'm assuming these are employees, to which employee has this dependent, and then the value for that, which is just the dependent's name. So what we've done here is we've split a single table into 2 tables to get it into first normal form. Now if we go back, let's say we lived in a country that limited the amount of children you were allowed to have. You would go to jail for the rest of your life if you had more than 3 kids, hypothetically. So we knew for sure no one's going to have more than 3 kids, because either one of 2 things. They don't, or if they do, we have to fire them because they have to go to the gulag. So we laugh, but that actually is the case in some countries. Well, it used to be. I don't know if it really is anymore. Our bigger problem now is actually population decline. It's like, come on, everyone, have babies. 2020, 2021 was actually quite shocking. The drop-off was like, I just hope I have a job in 18 years because there won't be any kids coming to college. Anyway, so you know you're not going to have that problem of Mary having a 4th kid. You know that's not going to be a problem. This is still not a good solution though, right? Because kind of like the issue where I talked about before, where you have with the 1-to-1 being problematic, you're going to end up having a whole bunch of blank fields here. It's a waste of space. It takes up a lot of data. But here, it's refined, it works well, it's doing it right. However, anytime I do a query on an employee, I'm going to be joining these 2 tables together to get their dependents. And even if they don't have dependents, I still have to look. So that's going to be work, processor work. So I'm trading off a waste of data, which is here in example 2, for a waste of processing here in example, this example. But because we, generally are not going to have that rule if you can only have 3 kids or you go to jail, it's generally a varying amount. You don't know. You have to do this. But I'm just illustrating this trade-off of processing and data. So let's, before we move into second normal form, let's talk about functional dependency. So functional dependency is where you look at the attributes themselves and you see, are they specifically tied to another attribute? Is my value as an attribute dependent on the value of another attribute? So going back to this example here, that for the first normal form, is Mary Smith, the value Mary Smith, her name, tied to her social security number? Yes. Mary Smith is 111-222-3333. So there is functional dependency there. So here we see an example where there is not functional dependency, where we see the supplier is not functionally tied to the product ID. So to get to first normal form, first of all, you have to be, second normal form, first of all, you have to be in first normal form. You can't have multi-valued attributes or varying fields. You can't have that. But then you also need to think about the functional dependency of each attribute. So here we see an example where the promotion ID and the promotion item ID has functional dependency on the promo price. So what you need to do is remove the regular price from this this table, because this table is a promotional offering table. So the only value that's directly tied to the promotional offering ID is the promotional price. The regular price is not functionally dependent on the promotion ID. Does that make sense? What they're saying is this should be stored in another table, because you may or may not have a promotion at any given time. Therefore, why would you have the regular price for only the items that are having a promotion? That's not consistent. So third normal form, first of all, you have to be in second normal form, and no non-key attribute is functionally dependent on any other non-key attributes. In other words, you may have it tied directly to the primary key, but it may also be tied to another attribute. No functional dependencies among any non-key attributes. Does that make sense? So while you may be tied to the primary key, you're also tied to another attribute, which is in violation of third normal form. So here we see an example where we have, this is in first normal form and second normal form. We don't have any thing where, I'm not tied to that primary key, or I have multi-valued attributes, and none of that stuff is there. However, I do have a field that is functionally dependent on other fields, which is the total amount. The total amount is based on the shipping plus the tax plus the item total, and this violates third normal form. So this is an interesting example that the author's giving, because that's technically a calculated field, which you can do as part of a query. You don't necessarily, you would never store this anyway. But I get what they're saying. Generally, when you do a third normal form example, you say this is where you would store this externally. One of the more common examples would be, so say you have a customer table, and generally part of a customer table is their address. Okay, so far so good. Is there any, in an address, are there any functional dependencies of those specific attributes, irrespective of the customer themselves? In other words, can I take a part of your address and figure out something else without knowing anything else about you? What could I use? Say you give me your zip code. Could I figure out your state and your city? Yeah. So in other words, that's a normal example they give. Wow, that's weird. Did it say bolt dying on it? I didn't even see that. I'll have to report that after class. So anyway, the typical example that I see is where they say you should pull out those other examples and make them part of a separate table. And good databases actually do that for addresses. I would say when I go and I fill in a field, it's pretty rare that, as a matter of fact, I get more annoyed than I should be the older I get, but it's pretty rare that they only make you put the zip code in. I think in the last year, I've seen it maybe 2 or 3 times total, and hundreds of times that I have to manually type in Virginia Beach, tab, scroll, VA, 23455. There's been a couple of times that it doesn't even they're grayed out, the city and state, that you can't even go in there. You type in the zip code and it fills it in automatically. What they did was they put their database in third normal form, and it's pulling from the other tables and automatically filling in the city and the state. I love that. I do that, I'm like, oh, you're a good business, I like you. You did your database right. But most of the time they're lazy, and don't even get me started about Bryce Ski Resort. That's just, she's the worst. I'm scared, gonna be bad stuff when I go there. Anyway, yeah. Again, we have the example here of moving it to another table, and again, we have the issue of more processing, but less data waste when you do it. So. All right, data types. Yeah.
Is it possible to put a table on a table?
I think that would violate the first normal form. Yeah, you should. You're thinking like a programmer now. And programmers, yeah, multi-dimensional tables, it would be a typical thing that you would do in a programming environment, but not in databases. All right, so I've talked about these before, data types, and these are proprietary to DBMSs. They each have their own set of data types, and when you build your table and design your table, you have to build it specifically for that DBMS. So these are these so-called primitive data types. They're supported directly by the DBMS. And you can have user-defined ones as well. So your standard primitive data types, date and time is one. Date and time is actually, technically speaking, a quantitative variable that's just a floating number. That's what it's actually being stored as, a floating number. So there is a start and an end point. You can't go literally any date. Like everything in computing, it's discrete. One of the most interesting examples I can think of with that, not necessarily database, but have you guys ever worked with dates in Excel? You know that there's an earliest date, right? And it's actually not that long ago. It's actually quite surprising how recent their earliest date is. It's 1900, January 1st, 1900 is the earliest date in Excel. So if you go before that, it's no longer a date and time type, primitive type. It's a string. The range is much wider in DBMSs. Like they'll go back, a couple thousand years and forward a couple thousand years, but it still is discrete. We have integers, small ints, big ints. So this is just the number of bytes that you use to store it. Whether you need to store billions or hundreds or thousands, that would be what you choose here. Floating variables. These are decimal values. Money. Yeah, there are currency data types. I generally dissuade students from using that because the formatting, indication that it's money is generally done on the API side and not so much on the database side. So it's okay, but I generally push students away from that when possible. Just use a float if you're going to be storing money values. Fixed and variable length. So these are varchars. Then we also have binary, where you can store kind of videos and pictures and things. Again, relatively rare that I've seen that. Generally, these have more pointers that point to these files as separate entities as opposed to entities within the database. I have seen instability I haven't tried it in SQL Server, but in Oracle and MySQL, storing large amounts of binary data, it actually does destabilize the database, and I've seen it stutter a lot using those. So again, from a practical perspective, probably not so much. So what are the ones that you really do use 99.9% of the time? Date and time, integers, floats, varchars. Those are 99.9% of what you were going to be using in databases. And it's interesting looking at this because these are none of what MySQL uses for its names for those things. It uses different names. Oracle uses these, but MySQL uses different words, which we'll get to. This is a DBA thing, protecting the database. Logging facilitates auditing later to see if there's been a break-in. So this is kind of a security side thing. Most security breaches are found post facto. You find out after the fact. And if you don't do this, if you don't do your logging, you may never find out. So this is an important thing to do. Update controls. So you do these things called backup and recoveries. These are temporal commands that run. Depends on the volume and type of database, but at least once a week, preferably every day. You'd run them at night. It will slow down the database, so there's kind of a debate as to when should you run them more or less. Generally, I see like every few days is a typical update cycle for that. Oh yes, I made it just in time, right at the end of class. Okay, so we'll have a case online, our virtual class on Thursday. We'll have a case that we work on. And then we'll do another mini lecture next week where I do the script, and we'll implement a little next Thursday.